Hello, my name's Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
Continue our commentary on TEMA, the 10th edition. In particular, today we're going to be looking at flow-induced vibration and see what TEMA has to say about that. And so you can see there's a lot of detail there. So we're going to jump into an area called Section 6. Okay, so we're going to start with these three sections, the scope, general, and discuss about vibration patterns. Talk about the scope. So TEMA says that fluid flow and complex geometry of the heat exchanger can cause the tubes to vibrate. And hence it's difficult to define because of these, complex parameters. TEMA goes on to say that even if you follow all these specifications that they've provided, that it's no guarantee, and TEMA will not cover the damage caused by vibration. They will provide is basic rules that are found, in literature that they've from their best of their experience. In general, they say vibration damage is caused by shell side flow relative to the baffle configuration and unsupported tube span. And if you go refer to table RCB 4.52, there's some information, design information. There's a caveat here. He says it does not consider flow-induced vibration problems. Let's talk about vibration patterns. This very broad grouping here. The first is the collision type damage when the tubes impact, for example, against the wall of the shell and tube exchanger or against each other, which is more common. You can get baffle damage, okay, from vibration, and you can get tubesheet clamping effect, which can cause because of tube joint leakage. You can have material defect propagation, and that can result in like a bending fatigue type situation. And then you have an acoustic induced vibration, which is like a gas column oscillation. Again, we'll get more into that a little bit later, but I just wanted to point out that the first four in the group is considered to be flow-induced vibration, while the group shown in green here is an acoustic, has to do with more with noise generated from the flow, gas flow, and that's sort of I consider that sort of they're separate phenomenon. Attention to collision damage, and we're going to dive into that subject. Okay, so tube can impact against each other. This is what we alluded to earlier about collision damage. It's the most common form. And it creates a flattening spot mid-span of the pipe, so of the tube. So that's where you're going to have the highest amplitude and the most likely chance of a tube impacting another one. And so if I draw a little picture here, the baffles are the green part and the tubes the red dotted lines. And then at the resting position, of course, everything's going to look like that. And then when we get vibration, we can get the blue lines are showing how the tube can vibrate potentially back and forth. Now, when you get them contacting each other, then that's called an interspan collision, and that's what we mean by this flattenings that can occur. because of their localized hammering, right? So the tube impacts the the baffle hole and creates like a tube thinning in that area. So that's where you'll get damage. And over here, this is another spot that can occur when you get a lot of vibration. You can get it's on down on the left side there, and that's a case where we can get sort of a phenomena of the tube thinning against the baffle inside the baffle hole. That's what I mean by that. Next, we're going to talk about the tube sheet clamping effect and that at the tube sheet joint leakage. Tube sheet clamping effect, it refers to the clamping effect that the tube sheet has on the tubes. So some of the benefits are that is, say for example, you need to increase the natural frequency of the assembly and to avoid a potential a natural frequency, like a problem with resonation, at the flows that are coming in, then you may choose to clamp the it down. So there's the benefit right there. It's a strategy. And the other one is the only problem is when you start to clamp the things down, then you get more lateral stress, especially at the exit of the tube sheet, and you can get potential breakage. Now we're going to look at material defect propagation and dive into bending fatigue. Got material defect propagation. So if we get an increase in flaws in a material are created, can create an increase in corrosion and erosion. So that these are some issues. So I'll want to create a drawing for you here, and I put one down so you sort of more understand what I'm getting at here. So if I have the red part there is the weld, and then I have a tube sheet, which is shown in orange, and then I have the tube itself. Now, this is where the tube is, where the weld is on the tube sheet is susceptible to defect propagation if the welds are not done properly. And so what I've done is I've shown a microstructure and I've superimposed what the grains would look like. So on the weld side, which is that triangular part over here, the what we get is like a Whitman-Staton grain structure, they call it, and that's an effect of fast cooling on the weld. And then we have a couple ferritic grain structures, like commonly found in low alloy carbon steels with low carbon content. And you can see that there's a difference in the grain structure, which will affect a few things like it'll add stresses to the part. So the tube sheets on the top and the tubes on the bottom and the welds on the right side. So right where they join on that V is where you have most susceptible to like a stress concentration at the root, because you might not have complete penetration of your weld and there's a stress riser there. And we've done some really good videos on in the past on fatigue, and there's a lot you can see if you look at our library on the topic. Thoughts about failure regions. They basically say failures can occur anywhere inside that heat exchanger. And they warn about U-tube bends because of their shape. They have a very low natural frequency, which means they can vibrate at and resonate and cause a lot of vibration related damage. You have a potential to do that. And they've got some interesting design tables on how to deal with that, and which are industry practices. Second is entrances, nozzle entrances, um, that with restricted areas, cross-sectional areas, have higher velocity. So that can create failure regions. Also, the tube sheet region, the unsupported tube span, especially near the entrances and exits. If you have a lower natural frequency, then you have a higher and higher excitation force, you can create a lot of problems in that area. Baffle regions, so unsupported spans, are susceptible to this kind of problem. Obstructions. So what happens with obstructions is it can increase localized turbulence, and these are in areas which you can't really avoid, like tie rods, impingement plates, and sealing strips, and those are additions. So what they try to do is it's a balancing act between, you don't want to have too many tie rods in because of these issues, but you need some. So it's an experiential type situation. Look at some design considerations or remedies to avoid that. TMAT has a lot of good advice. They say that the larger your diameter, the less problems you have with resonation and vibration, because the inertia is higher. And so what that does is, if you increase the diameter, then you get a larger moment of inertia, which can reduce that. But so they say, don't try to avoid using smaller diameters. But in industry, we tend to use 3/4 inch tubes is one of the most common used in the refinery industry, but they say to avoid that. Another thing they say is the unsupported tube length. First of all, they say limit the unsupported span. TEMA maximum span of less than 0.8. They can go into the tables, and if we have more requests, we can get into those design tables, and we can get into that and do some really cool examples. So next one is we can reduce the baffle spacing as a strategy. And the third one is you can reduce the cross flow. Design consideration are to change the tube pitch to reduce vibration. Another strategy is the redesign of the entrance impingement plates, and I think there's a little bit of discussion also about the exit design as well to reduce it. Also, the U-bend regions design consideration can help to reduce those issues as well. At the design consideration, looking at tube material thicknesses, as well as the baffle thickness and the tube hole size. Other strategy includes omission of tubes and the tube axial loading as well in their design.
I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.